everyone, welcome to episode 4 of Let's Talk Physics, and today we're actually going to be doing something different. We're starting out with an equilibrium problem and then transitioning into a dynamics problem. And so the first thing we have to talk about is what it means for these objects that we see here to be in equilibrium. By definition, that means that there's no net force acting on them in any direction, which means they're not accelerating. So if they're moving, they're going to keep moving at a constant speed, and if they're not moving, they're going to continue to stand still. And so what we have here are two objects, one with mass m and one with double the mass, 2m, connected by a string on a ramp. The string then extends from m around a pulley to an object of unknown mass, which we'll call capital M. And the question is, in terms of lowercase m and theta, what must the unknown mass be for the system to successfully be in equilibrium? And we can answer this question by looking at each object individually through free body diagrams. So if we look at the first object on the ramp with mass 2m, it's aligned like so. And we know that there's a point of contact with the string right here, which means that there's actually going to be a tension force, which we will call T1, acting along the ramp. Of course, the other force that's acting on the mass is gravity, and that's going to be acting completely downward. But as we said before, all the forces acting in a given direction will have to sum to zero. And so what we can do is, if this is the force of gravity, we can break it up, as we have in earlier episodes, into a perpendicular component and a parallel component. And so it's easy to see that the force of gravity acting in line with the tension force, because this angle right here is theta, is equal to Fg times sine theta. And so we can ignore this entire diagram and simply add a gravitational force acting downward along the ramp with magnitude Fg sine theta. Now, of course, you will have a force acting this way, which is Fg cosine theta, that's the perpendicular component, but by default, that's balanced out by the normal force acting upward. And so those are always going to cancel out and aren't the forces we're going to be looking at in this scenario. So what we can derive from this is that the sum of forces along the ramp, and let's just call that direction the x direction, which is T1 plus Fg sine theta, the sum of those two forces is going to have to be zero for the system to be in equilibrium. Now Fg is simply the mass times the gravitational acceleration, so this means that T1 plus 2mg sine theta has to equal 0. Now let's analyze the second mass on the ramp. It's going to be aligned the same way, and it's going to have mass m. We know that there are actually 2 points of connection with a string, and so there are going to be 2 tension forces acting on this mass. The one acting down the ramp is caused by the same string as T1, and so even though it's acting in the opposite direction, it's going to have the same magnitude T1 because it comes from the same string, which has the same tension throughout. Meanwhile, the tension force acting in the opposite direction we're going to call T2 because it's part of the second string. And now finally, there's also a gravitational force acting on this object, and so we're just going to call that Fg sine theta because it's also acting in line with the incline. And so what we learn from this is that the sum of forces along the x direction, which is equal to T2 plus the minus T1 plus Fg sine theta, is all equal to 0. And again, we can replace Fg with mg, so we have T2 minus T1 plus mg sine theta, all equals 0. And that's our second important equation. Now we only have one object left, and that's going to be mass 3 with the unknown mass. We know that there's one point of contact with a string, so there's going to be one tension force acting, and that's going to be upwards. And because it's the same string as the one that was causing the tension force T2, this tension force will also be T2. And it's also acting in a positive direction, so there's no need for a sign change. Meanwhile, in the opposite direction, we have the force of gravity, and since we don't have to break it up into components, there's no need to multiply by sine theta. So this equation will be rather simple. The sum of forces acting in this direction, which we will call the y direction, is going to equal T2 plus Fg, and will sum to 0. In other words, T2 plus capital Mg equals 0. And that's equation number 3. And it's important that we have 3 equations because we also have 3 unknowns. We don't know T1, we don't know T2, and we don't know capital M. And so in order to solve for any of them, we need to have 3 separate equations. And so here I've rewritten our 3 equations, and in order to solve for M, the first thing we do is we take our third equation and rearrange it. So we get capital M equals minus T2 divided by G. Next, we can take our first equation and solve for T1. We know that T1 equals minus 2mg sine theta. And using that, we can plug that into our second equation to solve for T2. T2 equals, well, if we bring T1 to the other side, that's going to be minus 2mg sine theta. And if we bring minus mg sine theta to the other side, well, that's just going to be minus mg sine theta, which makes this equal to minus 3mg sine theta. And now we can see that m, which is minus T2 over g, is really just 3m sine theta. And we found our unknown mass, which makes sense because this means that as the mass of the other 2 objects increases, the mass of the third object must increase to balance it. It also means that as the angle, or slope, of the incline increases, the unknown mass must get even larger to balance that, which is intuitively correct. Now we can ask, what would happen if we took this system in equilibrium and doubled the unknown mass? That means instead of having the unknown mass be 3m sine theta, it's now 6m sine theta. Well, intuitively we know that the system would no longer be in equilibrium. In fact, everything would kind of move this way, because the heavier mass would induce a larger force. And so to analyze this system and find the acceleration of each object, as well as the new tension in the strings, all we have to do is use Newton's second law. The sum of forces on a given object in a given direction is equal to the mass of the object times the acceleration in that direction. So if we look at our first object, for instance, we know that the sum of forces, which is T1 plus 2mg sine theta, is going to equal the mass, which is 2m, times its acceleration, which is a1. If we take our second mass, we know that the sum of forces acting on it are going to be T2 plus the negative T1 plus mg sine theta. And all that is going to equal the mass, which is m, times a2, its acceleration. And finally, if we look at our third object, the sum of the forces on it, which are T2 plus capital Mg, is going to sum to capital M times A3. And at first this might appear troubling, because what we have, instead of 3 equations and 3 unknowns, are 3 equations and 5 unknowns. We don't know either of the 2 tension forces, and we don't know any of the 3 accelerations. But we can fix this by relating the accelerations to each other. That is, because the first 2 objects are connected by a string, they must be moving and thus accelerating at the same rate. So we know that A1 equals A2. Similarly, the second object and the third object are connected by a string, but because the second object accelerates in the positive direction and the third object accelerates in the negative direction, we can set these equal to what we call minus A3. So basically we can say that the first equation equals 2ma, the second equation equals ma, and the third equation equals minus capital Ma. And now we have it all in terms of one acceleration, which means we have a total of 3 unknowns. So we can solve this system of equations. The first thing we do is realize that if we look at the first and second equations, the right-hand side of the first equation is double the right-hand side of the second equation, which means the left-hand side of the first equation, which is t1 plus 2mg sine theta, must be double the left-hand side of the second equation, which is 2t2 minus 2t1 plus 2mg sine theta. You'll notice that the 2mg sine theta is on both sides, so they cancel out, and we get 3t1 equals 2t2, or alternatively, t1 equals 2/3 of t2. So let's look at our third equation for a minute. We know that t2 equals minus capital Ma minus capital Mg. So we would know that 2/3 of t2 would equal this expression times 2/3. Now, using capital M equals 6m sine theta, we can see that this is equivalent to saying minus 4ma sine theta minus 4mg sine theta, because we distribute the 2/3. Now we also know that t1 is equivalent to 2/3 of t2, and so we can substitute here t1. And now that we know t1 in terms of just a, we can plug that in to the very first equation. So we have minus 4ma sine theta minus 4mg sine theta plus 2mg sine theta equals 2ma. Notice that from each term we have an m cancel out, and we also have a common factor of 2. So this minus 4 becomes minus 2, this minus 4 becomes minus 2, this 2 cancels out, and this 2 cancels out. Now we can bring all the terms with a onto the same side, so we have minus 2a sine theta minus a equals 2g sine theta minus g sine theta. And so 2g sine theta minus g sine theta is just a positive g sine theta, so this turns into a plus sign and this goes away. And now all we have left to do is factor out an a from the left-hand side and divide the g sine theta by the remains, and so we get a equals g sine theta over the remains, which are minus 2 sine theta minus 1. So because this is our value for a, this means that this is the rate at which the first two objects will now accelerate, and the opposite of this, which is g sine theta over 2 sine theta plus 1, is the rate at which the third object will accelerate. And if you wanted to, you could use this value to plug back into our equations and solve for the two tension forces T1 and T2 as I've done here. Now another way to get the answer to this problem is to use what's called the Lagrangian method. And if you don't know how that works, I highly recommend you watch the first episode of this series, where I go through every step of the Lagrangian process, and then come back to see this bit. For those of you who do know how the Lagrangian method works, let's get right to it. The first step, of course, is to define the Lagrangian, which is the kinetic energy T minus the potential energy V. And so the total kinetic energy of our system here will equal the kinetic energy of the first object, which is 1/2 times its mass, 2m, times its velocity along the plane. And so if we call the direction along the inclined plane x, its velocity will be the derivative of x with respect to time. And so that's just x dot squared. Similarly, for the second object, we add 1/2 times its mass times x2 dot squared. And for the third object, we add 1/2 times its mass, which is actually 6m sine theta, times its y velocity, which is y3 dot squared. Meanwhile, our potential energy V for the first object is m, is the mass 2m times g times y1, plus for the second object, its mass m times g times y2, and plus for the third object, its mass 6m sine theta times g times y3. Now that we've figured out our Lagrangian, it's time to find our constraint functions. And so these functions actually define the system we're in. And in this case, we know that one constraint function has to be y1 related to x1 by trigonometry. And so y1 equals x1 sine theta. And similarly, y2 equals x2 sine theta. Because recall that the x direction we're calling in line with the plane, and the y direction we're calling vertical. Now, because the first two masses are connected with a string, we also know that the distance between them will be held constant. In other words, x2 minus x1 is a constant. Similarly, because there's a string holding the second mass and the third mass together, but the second mass is moving in a positive direction when the third mass is moving in a negative direction, we can say that the sum of x2 with y3 is going to be held constant, because for every inch or meter or unit that x2 moves along the incline, that same amount of distance, the third object will move down vertically. And so their sum is a constant. So what I've done here is I've carefully rewritten our Lagrangian, and for every constraint function that we defined, I brought all the terms to one side, set that equal to 0, and called those f1, f2, f3, and f4. And so now is the fun part where we get to solve the Euler-Lagrange equations. And so basically for every variable, we have to go through this process, which is the partial derivative of L with respect to the variable, which we'll call Q, just to generalize, minus the full time derivative of the partial of L with respect to Q dot, plus lambda 1 times the partial of F1 with respect to Q,
plus lambda 2 times the partial of F2 with respect to Q, plus lambda 3 times the partial of F3 with respect to Q. And you get the idea, we add lambda 4 times the partial of F4 with respect to Q.
And so if we begin with the variable x1, partial L partial x1 is equal to 0 because L does not directly depend on x1 in any term. Partial L partial x1 dot is going to come from the first term, and we're going to get 2m x1 dot. And so because we take the negative time derivative, that's going to have a negative sign here and an extra dot on the x. Moving on to partial f1 partial x1, we see that that is equal to minus sine theta, so we subtract minus lambda 1 sine theta. Partial f2 with respect to x1 is 0. Partial f3 with respect to x1 is minus 1, so we subtract lambda 3. And partial f4 with respect to x1 is 0. And so all this is going to equal 0. Moving on to x2, partial L partial x2 is still 0. Partial L partial x2 dot now is m x2 dot. And again, we take the negative time derivative. Then we add lambda 1 times partial f1 partial x2. Well, that's just 0. Lambda 2 times partial f2 partial x2. That's minus sine theta, so we have minus lambda 2 sine theta. Partial f3 partial x2 is 1, so we add lambda 3. And partial f4 partial x2 is also 1, so we add lambda 4. And all this equals 0. Now we do the same thing for y1. Partial L partial y1 is minus 2mg. Partial L partial y1 dot is nothing. Partial f1 partial y1 is 1, so we add lambda 1. Partial f2 partial y1 is nothing, partial f3 partial y1 is nothing, and partial f4 partial y1 is still nothing. So this is just going to equal 0. Looking at y2, we have a very similar situation, where the partial L with respect to y2 is now minus mg. The partial derivative of f1 with respect to y2 is nothing. The partial of f2 with respect to the partial of f2 with respect to y2 is 1, so we add lambda 2. And the rest have nothing to do with y2, so all this just equals 0. y3 is the most complicated one. We know that the partial of L with respect to y3 is going to be minus 3 m sine theta g. And then we subtract the full time derivative of partial L partial y3 dot. And partial L partial y3 dot is 6m sine theta times y3 dot. And then we take the full time derivative of that, so we add another dot. Next, we look at all the constraint functions, and the only one that depends on y3 is the fourth constraint function, and the partial of f4 with respect to y3 is 1, so we add lambda 4, and all that equals 0. And using this set of 5 equations, we can get the same results that we achieved from the Newtonian method. The first thing we do is simplest. We just solve equations 3 and 4 for lambda 1 and lambda 2. So lambda 1 equals 2mg, and lambda 2 equals mg. With this information, we can use equation 1 to solve for lambda 3, so we get lambda 3 equals minus 2mx1 double dot minus lambda 1 sine theta, which is 2mg sine theta. With that information, we can use equation 2 to solve for lambda 4, which looks something like this. Lambda 4 equals mx2 double dot plus lambda 2 sine theta, which is mg sine theta, minus lambda 3, which is going to be plus 2mx1 double dot plus 2mg sine theta. And finally, we can use this definition of lambda 4 to plug it into our last equation and get everything in terms of just constants and accelerations. There was one slight mistake here, though. This should actually be minus 6m sine theta g, and minus 6m sine theta g y3 up here, because 6m sine theta was the mass of the original object, not 3m sine theta. And so we can continue to rewrite this as minus 6m sine theta g minus 6m sine theta y3 double dot plus lambda 4, which is mx2 double dot plus mg sine theta plus 2mx1 double dot plus 2mg sine theta all sums to 0. And so I've rewritten it here, and what we can see is that this 3mg sine theta over here combines with the minus 6mg sine theta on the left to form minus 3mg sine theta. And so the next step is to realize that because the distance x1 and x2 travel have to be the same, their velocities and accelerations also have to be the same, and so x2 double dot equals x1 double dot. And y3 double dot has to be the same in magnitude, but is opposite in direction because it goes negatively. So y3 double dot is equal to minus x2 double dot and minus x1 double dot, which means we can rewrite this as minus 3 mg sine theta minus 6 m sine theta y3 double dot minus m y3 double dot minus 2m y3 double dot, all sums to 0. So all I've done there is replaced x1 double dot and x2 double dot with minus y3 double dot. We can then isolate the terms containing y3 double dot, so we get 6m sine theta y3 double dot plus what's going to be 3my3 double dot equals minus 3 mg sine theta. So notice that there's a factor of 3 in each of these, so this turns from a 6 to a 2, and the other 3's cancel. And so if we factor out a y3 from the left-hand side, and then divide the right-hand side by the remains, we have y3 double dot is equal to minus mg sine theta over the remains after factoring out, which is going to be 2m sine theta plus m. And notice how there's a factor of m in each of these. So this is actually equal to minus g sine theta over 2 sine theta plus 1, which is exactly the same result we arrived at using the Newtonian calculation, except now we have the negative in the numerator instead of distributed to the denominator. Now, if you were vigilant, you might notice that this is actually the opposite of the result we got using the Newtonian method, in that we said that this was the acceleration for the first two objects, whereas now we're saying this is the acceleration of the third object. But really it's not, because when we did it using the Newtonian method, we let g equals minus 9.8 meters per second squared. Whereas here, we said that the potential energy V equals mgy. But the potential energy has to get bigger as y gets bigger. And the only way for that to happen is if we let g equals positive 9.8 meters per second squared. And so even though the way it looks right here seems opposite to the answer we got using the Newtonian method, it's actually just because g has a positive value rather than a negative value in this case. Now, if you were looking to find the tension forces using this method, that's not that hard either. Because our third constraint function claimed that the distance between x2 and x1 was always a constant, in a sense it represented the string connecting them. And if you look at our value for lambda 3, and you plug in the opposite of what we found for y3 double dot in the place of x1 double dot, you will find that it's the same exact result as we found for the first tension force using the Newtonian method. However, g is still positive 9.8 meters per second squared in this case, which makes it look like the opposite answer, and in a sense it is, because in this case lambda 3 represents the first tension force pulling object 2 down the ramp, rather than the force pulling the first object up the ramp. If we're looking for the second tension force, we look at our fourth constraint function, which in a sense represents the second string, which connects object 2 with object 3. If we look at our value for lambda 4, we see that mx double dot combines with 2mx double dot to form 3mx double dot, and mg sine theta combines with 2mg sine theta to form 3mg sine theta. Once again, if you substitute the opposite of what we found for y3 double dot in the place of x double dot, you will find that we get the opposite answer of what we received using the Newtonian method. And this is just explained by the fact that g is now 9.8 meters per second squared rather than minus 9.8 meters per second squared. Make that change, and you have the same exact answer as we got the other way. So So that's pretty much it for this episode, guys. I hope you enjoyed it, because it was a lot of fun to make. If you want to see me make any more videos or have any other thoughts, feel free to let me know in the comments below, and I will see you all next time.